Hello, welcome. In this video, we're looking at 2D matrix transformations. It's a really enjoyable topic. And before we really get to it, let's just check in on our notation. This is one way to write matrices using these parentheses here. And this is what I will typically use. You can also use these kind of squarish brackets, but be careful not to use these vertical lines. That represents a determinant in matrix algebra and not a matrix as we're using today. So be aware this is something else. We're using these two types of notations, primarily this one right here. So watch out for those vertical lines. As far as transformations go, what we'll do in this video is we'll start with our transformation matrix, whatever it is. In this case, I'm using the letters A, B, C, and D. It's some matrix that transforms some thing, some object, in this case maybe a point or a vector, and then we're going to get our object after it has been transformed. So we're going to put the matrix in the front, then follow it with the object, and then get our transformed object at the end. I also want to point out that you could definitely reverse this order. It might change some of the ways that you notate your matrix transformations and the values you even use, because if you put your object first, notice that in this case with the point, you have to write it as a 1 by 2 matrix, not a 2 by 1 matrix, because in order for the matrix multiplication to work, you need to have this row multiplied by this column here, and that won't work if you have it written vertically like we did in the last one. So you can put your object first, and then you can put your transformation matrix after that. Of course, in the end, you'll still have your transformed object, but the idea is that this can change some of the values of the transformation matrices, because matrix multiplication is not commutative. So if you change this order, be aware it might change the values of your transformation matrices. So again, we're going to do it this way. We're going to start with the transformation matrix, then our object, and then our result. All right, so let's look at some examples right away. Let's say we have a point 2, 1, and I want to think about a matrix impacting the location of this point, either rotating, reflecting, dilating, doing something to it. So what I usually do is I set this up. This is my structure. And I think about some kind of a transformation, something that's familiar. Let's say a rotation of 90 degrees. So I'm rotating 90 degrees, and the default is counterclockwise. And with a simple example, either in my head or on paper, I'm trying to think, what's my matrix that will help me do this? Well, I take 2, 1, and I know that if I rotate it by 90 degrees, I'm going to get to negative 1, 2. And we notice that our x and our y values are rotated to negative yx. And in general, capital R for rotation, rotating by 90 degrees, a point xy, that point will become negative yx in order to accomplish that rotation. That's what this is saying. So how can we use that to our advantage? Well, if we look up here at the structure of our equation, we've got to pick values of a and b and c and d, so that when we multiply them by x and y, we get a transformed point that equals negative y on the top and x on the bottom, right? xy has to become negative yx. So the question is, what value of a and b will give me a negative y up here? Well, I've got to have a 0 for a, because to get negative y, I can't have any x, and I've got to have b equal negative 1. On the bottom, I've got to get an x, right? Because it has to be the point negative y up top, x in the bottom. Well, to get x in the bottom, I need 1 for c, and I don't need any y at all, so d is going to be 0. In other words, I think about the resulting transformed object, what it is, and the values of a and b and c and d that get me what I want. So in order to get to negative y and x, I know that a needs to be a 0, b needs to be a negative 1, c needs to be 1, and d needs to be 0, and this is my matrix. And then what I might do is just take this matrix and then multiply this matrix by xy and see what happens. And I encourage you to pause the video and do that. If you take this matrix and multiply it by xy, you'll see you get negative yx. And take your time and do that. It's really important, because that's how a lot of the intuition is built. All right, let's look at some other basics here. Of course, you don't have to move a point at all. And in that case, you're just at the point xy. That can be accomplished through what's called a null transformation using the identity matrix. Now, you might pause the video and think about it. what kind of a matrix can I multiply by a point xy and still get xy at the end? I'll give you a hint. It's definitely not all ones, and it's definitely not all zeros. If you set it up, this is what the matrix will look like. And in general, identity matrices have these diagonals of ones, and then everything else is a zero. And that, if you do the matrix multiplication, you'll see that nothing will change in the x and the y. For the 90 degrees, we just saw that one. There's our matrix. Okay, how about this one? Right, we're going right through the origin there, so it's a rotation of 180 degrees or a reflection through the origin. Those are the same, logically equivalent in 2 dimensions. Interestingly, in 3 dimensions, and we'll get there, those are not necessarily the same thing. But for now, you can see that 2 and 1 become -2, -1. So xy becomes negative x, negative y. And if we set up our structure of multiplication, we can see that these have to be the values of a and d. A has to be -1, and d also has to be -1. And again, that's only to get from xy to -x, -y. And if you're not convinced of any of these, set them up. And if you want me to, let me know, and I'll show you that example in detail. Over here, we're going by 270 degrees, or I was going to say going the other way, going 90 degrees. But it's a 270 degree counterclockwise rotation, and you can see that xy, it becomes a 2, 1, we get 1, -2, so it becomes y, -x, and that's accomplished with this matrix right here. So if you take this matrix and multiply it by xy, you will get the point y, -x, and that's the idea of each of these. What about this one? Here we've got a point. What are we doing to it? Well, we're reflecting it over the line y equals... No, we're reflecting over the line of the vertical axis, the y-axis. Sorry, it took me a little time to say. And if we look at what's happening, 2 is becoming -2, but the height is remaining the same. So we need a matrix that when we multiply it by the point 2, 1, we get -2, 1. Or we multiply xy, our matrix by xy, we get -xy. All right, so a reflection in the y-axis takes a point xy to the point -xy. How can we do that? We can do that if we multiply by this matrix, right? -1, 0 times xy, that becomes -x plus 0y, or -x. And then 0, 1, our second row by our column, that becomes 0 times x plus y. That gives us our y value. So we start at xy, and we end up at -xy. Boom, we've got it. So this is our matrix that accomplishes a reflection over the y-axis. What about the x-axis? Going the other way, it's very similar, except now the -1 is here. And that's a really nice thing about these transformation matrices. You might notice they're really just made up of ones and zeros, positive and negative ones and zeros. And that's pretty much true until we get to dilations, which we'll do in a moment. All right, so this reflection right here, what are we reflecting over? Well, the mirror image is like right here. It's the line y equals x. As you might know, when we reflect over the line y equals x, every point xy reverses. It becomes yx. So the matrix that does this is this one. And you could test it, right? You don't have to memorize it. You could memorize it, I suppose, but you don't need to. You do 0, 1 times xy, and that gets you 0x's plus 1y. That's just a y up top. And then our second row times the column gets us 1x on the bottom. So we start off at xy. We multiply our matrix by this point, and it reverses it. It reflects it over the line y equals x. All right, here are the dilations. Now, obviously, you can rotate around other lines and that other than just y equals x, and that might impact the ones and zeros as well. But right here, this is our first example. We're having something other than a 1 or a 0. And you might notice that our point A has been transformed to this image right here, and x is going from 2 to 6. So we definitely have a dilation in a horizontal direction by some value, and that means we're multiplying our x value of our point by k. In this case, 2 is being multiplied by 3. And this is how we accomplish it, right? 3, 0 times xy becomes 3xy, or in our case, 3 times 2, 6, and then 1 times y, or 1 times 1, which is 1. That gets us the point we need. So we can dilate horizontally with this matrix right here. As you might not be surprised, a vertical dilation, which changes the y values in our points right here, multiplies a point xy, multiplies just the y value by k. Our matrix that accomplishes it, it just reverses those two numbers. and that's our matrix for a vertical dilation. What if you want to do both? Well, if you want to combine this, you just multiply both x and y by that k value. It becomes your scalar, and hence the name scalar multiplication. And that can be accomplished by this matrix right here. We have 3, 0 times the column xy. That gives me 3 times x plus 0y, or 3x. And then likewise, we have 0, 3 times xy gives me 0x plus 3y, or 3y in the bottom. It triples the x's and y's and dilates our matrix both vertically and horizontally by k. So I really encourage you, when you're thinking about matrix transformations in 2 dimensions, think about it in terms of some kind of point. Try to maybe generalize it algebraically. Write down the structure here and solve for A, B, and C, and D to get what you want. All right? But what's really cool about this is that you can actually apply this to shapes as well. So I encourage you to pause the video and set this problem up. Try it, A, B, C, and D. See if you can do these things, and then come back together and we'll solve it. Okay, so let's work on this together. In part A, we need a matrix to represent our given triangle. In all of our problems so far, our points have been these things that we are transforming, and they've been these single columns, x's and y for 1 point. So you might imagine with 3 points, we have 3 columns, and that's exactly what we have here. This is the point A, second column is the point B, and third column is C. Next, we want to transform it. We want to dilate it horizontally. And you might remember to do that, to dilate a point xy, we were multiplying x by k. And the matrix essentially was a k over here, the scale factor here by a. D was 1 and B and C were 0. Well, the same is true here. If you want to convince yourself of this, just take a single row, this right here, 3, 0, and multiply it by the first column. What you'll see is 3, 0 multiplied by 3, negative 2, gets you 3 times 3, or 9, plus 0 times negative 2, 0, and that 3 becomes a 9. In other words, the 3 is tripled, and the negative 2 is not changed at all, because eventually, when we multiply 0, 1 by this row, we're going to get 0 times 3, 0, plus 1 times negative 2, which is negative 2, and this is going to become 9, negative 2. Likewise, the 1, 7 becomes 3, 7, and the negative 4, 2 becomes negative 12, 2. These 3 points have been dilated horizontally by a scale factor of 3. Pretty cool stuff. Next, we want to rotate the matrix. We want to rotate it, the triangle, by 90 degrees. So here's the original triangle. I left up here the horizontal dilation in case you write that down. This is the work now for the rotation. We need some matrix so that when we multiply it by our points in our triangle, it's rotated by 90 degrees. So what I often think of is, okay, what does a rotation of 90 degrees entail? Well, it takes points x's and y's and it swaps it, so it's negative yx. So instead of 3, negative 2, that's my x and y, I'm going to swap those numbers and take the opposite of the y value. So that would become positive 2, 3, negative 7, 1, and negative 2, negative 4. So I know I need to get to this right here. That's my goal. So how can I do that? Well, the original matrix that would do that, in order to swap these two, was 0, negative 1, 1, 0. And that's exactly what happens here, right? The fact that we have more points that are multiplying our we're transforming here doesn't impact the actual matrix itself. It's still the same transformation matrix. Pretty cool. Now, in part D, it says find the image of the triangle after it is dilated and then rotated. Notice here this is a composition notation. So in a composition, it's the dilation that comes first and then the rotation, which is not what we have here, right? We've dilated our triangle to this, and then we separately rotated it, the original triangle, with this matrix. Now we want to dilate it and then rotate it. And we want to be careful about the order, because it might not necessarily be the same thing. If we dilate and then rotate, or rotate and dilate, we want to do exactly what they're asking. We want to dilate it first and then rotate it. So how can we accomplish that? Well, as you might suspect, even though matrix multiplication is not commutative, you might be aware that it's associative. So we can put them all together in the same equation and just group them in the appropriate way to get the right answer. And that's all we have to do. Notice here's my triangle matrix right here. So I put my dilation first. It's the first thing I'm going to multiply it by. And then I'm going to multiply it by my rotation matrix here. So what are my options? Well, it's associative. So I could multiply my two transformation matrices first, and then take that result and multiply it by this triangle matrix here. I could also multiply my triangle matrix by the dilation matrix first, and then multiply the rotation matrix by that result. I just can't skip around. I can't like do the rotation times the triangle and then times the dilation. That might mess me up. But I can group it. I can associate it. So here, what I did to show you this is I first dilated my triangle. Okay, there's my dilated triangle. And now I'm going to rotate. I'm going to swap these numbers and take the opposite of the y value. So this will become 2, 9, negative 7, 3, and then negative 2, negative 12. And this is where the triangle will now live. Of course, it's really fun to combine or multiply or associate these two matrices first to see what other kind of matrix can accomplish both transformations in one. And it's really always delightfully surprising to me how this works. And here you kind of see the grouping of these two matrices together. I've multiplied my rotation matrix by my dilation matrix, and this is what I get. So this will accomplish the same exact thing. Now, I also want to make sure you have a way of checking your work and working through this other than just using maybe pencil and paper. And one great resource that you have is this free calculator, GeoGebra. So I'm going to just show you some quick ways to deal with this in GeoGebra so you have some extra support. So I would start by just plotting my points. So 3, negative 2, there's A. This is my triangle. B equals 1, 7. And then C equals negative 4, 2. Now I could take these 3 points, I could type in the command polygon. I want a polygon list of points. Okay, so A, comma, B, comma, C. All right, there's my triangle. It gives me the lengths of the segments. I don't need that, but this I will need is the name of the polygon. And now I want to enter in some transformations through matrices. So I'll do my first matrix, and I'll call that my dilation matrix. The notation for that is these curly brackets, and then I enter it by row. So my first row and then my second row. So, and I can enter this triangle as a matrix as well. I just wanted you to see how I can enter it using points, but I'll show both ways. So what we have a dilation matrix and then a rotation matrix, right? So the dilation matrix was 3, 0 on the first row, and then the second row was 0, 1. Now when you hit enter, you get that nice matrix notation. Okay, so that looks correct. And if you need to edit it, you can just click on it and then change the numbers. My second matrix is the rotation matrix. So my first row, I've got 0, negative 1, and then my second row, I've got 1, 0. And again, if you ever get stuck on this, just put an XY here in your head to see what's happening. You'll see how this multiplication gives you the negative YX. All right, so we've got these two matrices, and I just want to see what's going on. Like, how does it transform this shape? And is my work correct so far? So one way we can do this is type in the command apply matrix. So there might be another command to combine multiple matrices at once, but this just does it one at a time. So the first thing I want to do is dilate it. So m_1, and the object I'm dilating is called T1. So there it is, a dilation of horizontally of our triangle. So like C was at negative 4, we've dilated by 3, so now it's at negative 12. B over here as a distance of 1 is now at 3, and then A was at 3, now it's at 9. And then what we can do, this shape has a name, let's find it, it's T1 prime. We can apply the matrix again. We could apply the other matrix, excuse me, to see if it gets the same result. I think I pressed the wrong button, it's angry at me. Okay, there we go. So our second matrix is the rotation matrix, but this time we want to apply it on the triangle that's been dilated. So that's T1 prime. And I'll zoom out a little bit. Okay. So T1 double prime now. You can see the point. This is the point A double prime, or 2, 9. B is at negative 7, 3. C is at negative 2, negative 12 down there. And those are exactly the points that we got. Now, let's say you don't want to do it that way. what you could do is enter your triangle matrix and then perform the multiplication directly. So that's the last thing I'll show you. I think I'll just do it right down here since I already have the other things entered. I'll call this triangle matrix T, and I'll choose the rows that we had before. So my first row, the x values of the points, 3, 1, -4. And then the second row are the y values, -2, 7, 2. Okay. So there's my triangle matrix, and I can have a value p or something, and I can just make it m2, the rotation matrix, times m1, the dilation matrix, times t. Right? And there's the result, 2, 9, -7, 3, -212, which is exactly what we got. We often talk about transformations and the rotations of 90 degrees, but it must always be kind of in the back of your mind. What about turning other amounts? What can we do? Well, like many things in math, if we want to figure out something more complicated, we want to reference something that we're familiar with. So let's go back to the 90-degree rotation and try to look at it from a more trigonometric perspective to understand in general what's happening here. So if I have a point xy and I'm rotating by 90 degrees, it becomes -yx. Got it. But I want a matrix that takes a point and turns any degrees or any amount of radians that I tell it to. So we look at our setup here. Like, this is what we had for the matrix that turned at 90 degrees. Now to turn, you might have some familiarity with parametric equations or other things. Turning often involves sines and cosines. That's exactly true here, right? Think about cosine and sine. Where are we going to put them in our matrix? Well, we know that the cosine of 90 degrees is 0. So maybe you wouldn't be surprised if we can turn other angle amounts by saying the cosine of whatever angle we want goes here, and amazingly, here as well. But what about the sine? Well, the sine of 90 degrees is 1, right? So maybe it's not so surprising that in this spot, that this element will be the negative sine of the angle, and this is the positive sine of the angle. So for turning 90 degrees, this is actually another way to view the matrix that shows us what we're doing. And that's really great because instead of 90 degrees, we can put in any angle amount there. And this matrix will allow you to rotate by any angle. How cool is that? And here I set something up in GeoGebra. I just graphed some random points using the tools here. And then I made a slider, and here's that matrix, and I'm just going to turn it. Right? I can turn it by any amount now. And that's all through the matrix work here. And I thought you'd appreciate that. All right, well, this is an introduction to two-dimensional transformations with matrices. I hope you enjoyed it. Thank you.